Join us on Patreon and become part of our journey to uncover history's untold stories. Your support helps us create in-depth content, bring hidden narratives to life, and keep history alive for everyone.
Throughout history, humanity has strived to construct architectural wonders that withstand the tests of time and nature. Among these marvels, the temples of ancient Greece stand as enduring testaments to human ingenuity, skill, and resilience. The ruins of structures such as the Parthenon, the Temple of Hephaestus, and the Temple of Apollo at Delphi continue to evoke awe, not only for their aesthetic grandeur, but also for their remarkable durability. The lands of Greece, positioned along the seismically active Aegean Arc, have long been plagued by earthquakes. Despite these geological challenges, many of their temples have survived centuries of tremors, invasions, and environmental decay. This resilience was no accident. It was the result of meticulously calculated engineering, advanced construction techniques, and an intimate understanding of the forces of nature. The architects of ancient Greece were not merely artists. They were scientists, mathematicians, and engineers who meticulously designed temples that could endure the violent shaking of the earth. Their methods, though developed over 2 millennia ago, incorporated sophisticated principles that modern seismic engineers continue to study. But how did they accomplish such a feat? What knowledge did the ancient Greeks possess that enabled them to build structures capable of withstanding earthquakes? This article delves into the secrets of Greek temple construction, exploring the materials, architectural design, and technological advancements that contributed to their remarkable longevity. The Greek mainland and its surrounding islands sit upon one of the most seismically active zones in Europe. This region, part of the broader Mediterranean seismic belt, frequently experiences tectonic shifts due to the African plate subducting beneath the Eurasian plate. The energy released by these geological movements manifests as earthquakes, some of which have been catastrophic throughout history. Ancient Greek builders had to account for these conditions when designing their temples, ensuring that their structures would not crumble under the force of nature. Despite the immense risks, the Greeks did not abandon their vision of monumental architecture. Instead, they adapted their construction techniques to mitigate seismic damage. This adaptation was not instantaneous, but rather the result of centuries of accumulated knowledge, trial and error, and observation of nature's impact on early structures. Through continuous refinement, Greek architects devised innovative methods that would ultimately lead to the development of structures that could stand firm against earthquakes. One of the key factors behind the earthquake-resistant nature of Greek temples was the careful selection of building materials. Greek architects primarily relied on locally sourced limestone and marble, materials that, when used strategically, could enhance a structure's stability. The choice of stone was not arbitrary. It was based on the understanding of how different materials responded to stress, pressure, and seismic activity. Marble, prized for its strength and aesthetic appeal, was often used for temple columns and decorative elements. However, pure marble is relatively brittle, which could make structures vulnerable to sudden shocks. To counteract this, Greek builders often employed limestone as a foundational material. Limestone, while softer than marble, possesses a higher degree of elasticity, which allows it to absorb and dissipate seismic energy more effectively. This dual material approach gave Greek temples a level of flexibility that helped them endure earthquakes without catastrophic collapse. Additionally, Greek builders utilized wooden reinforcements, particularly in the roofs and joint structures of their temples. Unlike stone, wood has a high degree of elasticity, which made it an ideal material for absorbing seismic forces. Some temples, such as the Parthenon, were constructed with wooden dowels and metal clamps embedded within their stonework. These clamps, often made of iron or bronze, held blocks together while allowing for slight movement, thereby reducing the risk of sudden fractures during an earthquake. Greek temple architecture was not only about aesthetics but also about function. The structural integrity of these temples was enhanced through various architectural techniques that minimized earthquake damage. The use of entasis, stylobates, and columnar spacing contributed to both the beauty and resilience of these buildings. Entasis, a subtle curvature applied to columns, prevented visual distortions and also served a functional purpose. By slightly bulging in the middle, columns distributed weight more efficiently and could better withstand lateral forces exerted by earthquakes. Additionally, Greek architects recognized the importance of column spacing and seismic resistance. Rather than placing columns too close together, they allowed for sufficient gaps to prevent the progressive collapse of a row of columns in the event of ground movement. Another major feature was the use of a flexible foundation. The Greeks often constructed their temples on layers of compacted gravel or bedrock, which helped distribute the force of seismic waves more evenly. The stylobate, or temple platform, was designed with slight convexity, ensuring that water drainage did not undermine the foundation while also allowing the structure to settle naturally over time without forming cracks. One of the most remarkable aspects of Greek temple construction was the precision with which stone blocks were cut and assembled. Each block was meticulously shaped to fit its corresponding piece, creating an interlocking system that provided additional strength. The method of anatherosis, in which blocks were smoothed and fitted together with extreme precision, eliminated the need for mortar. This drystone technique allowed for slight movement between blocks, reducing stress during an earthquake. Greek architects also employed modular construction techniques, meaning that temple components were built in sections and assembled systematically. This approach not only expedited construction, but also allowed for easier repairs when damage occurred. The use of modular components meant that a single damaged section could be replaced without compromising the integrity of the entire structure. The earthquake-resistant techniques pioneered by the ancient Greeks did not disappear with time. Rather, they laid the foundation for later architectural advancements in the Roman, Byzantine, and even modern eras. The principles of flexibility, weight distribution, and material selection continue to influence contemporary seismic engineering, particularly in earthquake-prone regions. Modern studies of Greek temple ruins provide invaluable insights into ancient engineering prowess. Engineers and architects today still reference Greek construction techniques when designing earthquake-resistant buildings, recognizing the wisdom embedded within these ancient structures. The Parthenon, though partially ruined, remains an enduring symbol of architectural resilience and a testament to the ingenuity of the Greeks. The resilience of Greek temples in the face of earthquakes was no mere coincidence. It was the result of deliberate engineering decisions, innovative material use, and a profound understanding of seismic forces. Through centuries of observation and experimentation, the ancient Greeks developed architectural techniques that not only ensured the longevity of their temples, but also influenced generations of builders who came after them. Their mastery of earthquake-resistant construction stands as a legacy of human ingenuity, an enduring reminder that even in the face of nature's might, the brilliance of engineering can ensure the survival of civilization's greatest monuments.